Alright, so a coordination compound is also called a complex ion. It's a transition metal ion that has ligands attached. So our transition metals, because they have d orbitals and some of them have access to f orbitals, they can form these very complex ions. So it's still a substance that has a charge, because that's what an ion means, but it also has other things attached to it, kind of like a polyatomic. A ligand is a Lewis base, which means it can accept an electron pair. It's a molecular ion having a lone electron pair that's donated to an empty orbital on the metal ion to form a covalent bond. Make sure that you know the definition of ligand, make sure you know the definition of a complex ion, and just the word ion itself. We know that something is a complex ion when in the formula it has a bracket around it. That the bracket represents the complex ions. So instead of parentheses, you're going to see brackets around it. Alright, so here's an example. We have cobalt in the middle, which is a transition metal, and the ligands that are attached are ammonia molecules. 1, 2, 3, 4, 5, 6. So notice it has 6 things around it. Even though it has already bonded with 6 ammonia molecules, it's still carrying a +3 charge, which means it can still bond with something else. How many ligands are attached to the metal depends on the metal, and the number is called the coordination number. So for example, copper with a +1 charge can have 2 ligands or 4 ligands. Silver can have 2 ligands. Gold can have either 2 or 4. So as you're looking at this chart of typical number of ligands, notice that 4 and 6 are the most common types or common numbers for amount of ligands. Alright, before we really delve into how to name ligands, I do want to make you aware of some common ligands. So we know that H2O is water, and so water is the common name for that formula. So there's some common ones here too. Oxalate, ethylene diamine, which is abbreviated EN. There's another one, DEN as an abbreviation. EDTA, if you've ever heard of that, in earth science, is a complex ligand. So when we go to name things, these common ligand names might pop up because they have special names of themselves. Alright, so the rules for naming complex ions. As with any ionic compound, you always name the cation first before the anion. Remember, the cation is the positive thing, the anion is the negative thing. So you always start that way. If there's not a charge shown, you name the positive thing first, then the negative thing. When you're naming the complex ion itself, the ligands are named before the metal ion. When you name the ligands, an O is added to the root name for the ion. So instead of ending things in IDE like you're used to, we're going to actually end it in O. So for the halides, remember that's group 17, instead of saying fluoride or fluorine, we're going to say fluoro, chloro, bromo, ido. Hydroxide would become hydroxode, cyanide would become cyanode, etc. If it's a neutral ligand, however, like water, ammonia, nitrogen monoxide, those have specific names to use, which are listed in a chart at the end. If there's more than one of these ligands, so let's say there's 2 fluorines as a ligand, then you're going to use the prefix di, so it would be difluoro. You can also use bis, tris, or tetrachus if it's a more complicated ligand or it already contains the common prefixes mono, di, tri, tetra. The oxidation state which remember is simply the charge on the metal, is designated by a Roman numeral in parentheses. So we're going to name the ligands using prefixes to tell how many. We're going to name the metal, and then we're going to put the Roman numeral to tell us the charge that's on the complex ion. When there's more than one type of ligand present, they're named alphabetically. Prefixes do not affect the order. If the complex ion is a negative charge, then the suffix "ate" is added to the name of the metal. Sometimes the Latin name is used to identify the metal. So if it has a Latin name, which is where we get the symbol from, that's the name that we're going to use. Alright, so here's your chart. If it's a neutral ligand, then you're going to use these words as opposed to just putting an O at the end. Aqua, amine for NH3, methylamine, carbonyl, nitrile. So these last three, or these middle two right here, those come from organic, which we're going to do in the next couple days too, so these names might become more familiar. And then here are the ones that you would just list as an O. So if it's an anion, typically then you just attach an O to the name. Now if it's a negative complex ion, then the metal might use the Latin word. So here's our list of metals that have Latin words if the complex is negative. Alright, so let's just dive in and start doing some examples so these rules might make more sense. So if we see this, I would automatically recognize this as a complex ion because I see the brackets and there's a charge. So this is not a neutral compound, so I don't have to worry about naming the cation first and then the anion because it's an ion. So we're going to name the ligands first. Here is my metal, so these things in here must be the ligands. NH3 is a neutral compound, so I'm going to use that special word from the chart. Cl is an anion, so I'm going to change it to end in O, chloro. Now because I have two different ligands, I want to make sure that I name them alphabetically. So amine, starting with the A, would come before chloro, starting with the C. Because I have 5 NH3s, I'm going to want to use the prefix penta. So this would be named pentaamine chloro. Notice that it's all one word here. Ru is ruthenium. And then I need to figure out the charge that is on the metal. So that comes to oxidation numbers. Whoops. We know that this is neutral, so this is not going to contribute to the overall charge at all. I know that chlorine, being in group 17, has a -1 charge. Well, all of these charges are going to add up to -2. So what does the charge on Ru have to be? Well, it would have to be a 3. So I'm going to put the Roman numeral for my metal as 3. And then because this is not a neutral compound, this is an ion because it had that charge there, I'm going to put the word ion. If we look at another one, we have FeCN6 - 4. Notice that this ion is a negative charge. I guess we can put some brackets around here. This one was positive, so we didn't change the ending on the metal. This one is a negative, so the metal has to end in ATE unless it has a Latin word. Since we call Fe iron and it doesn't match the symbol, I know there's a Latin word to use instead. I have 6 CNs, so I'm going to say hexa. CN is cyanide, so I'm going to say cyanode, changing it to an O. And then the Latin word for iron is ferrate. If I look at my charges to figure out the charge on the iron, cyanide is a -1, and I have to make it equal -4. So that means iron here has to be a +2. And again, because it's not neutral, I'm going to add the word ion. So let's try one that's not an ion. K2PtCl4. So here I have my brackets, and I have something on the outside of the brackets, and there's no charge. So I know that this is a neutral compound. So I'm going to name the cation first. So the first thing doesn't have the brackets around it. The first one's always your cation. So K is potassium. So I'm going to say potassium as my first word. And then the complex ion is going to be my anion, so that's going to be my second word. I have 4 chlorines, so I'll say tetra, chloro. PT is platinum. It's not, the word platinum matches the symbol, so it's not Latin. So I'm going to change the end of the word platinum to ATE because it is the anion. PLATIN, platinate. Now I need to figure out the charge on platinum. Well, if I uncross my charges, then I would know my complex ion had to have a charge of -2. I know that chlorine carries a -1 charge. There's 4 of them, so that's really like saying a -4. So that means the platinum must have been a 2. And because this didn't have a charge to begin with, I don't need to add the word ion to the end. Let's do one more and then we'll do this backwards. Okay, so here we have a case where there's no charge, so this is a neutral complex ligand. I have 2 ligands, so I need to make sure I name these alphabetically. Here I have NH3, so that is amine, and NO2, which is nitrite, so I'm going to call it nitro. So amine would come first, so I'm going to say triamine, trinitro. The element is cobalt. And then I need to figure out the charge. Well, this has a charge of 0. NO2 has a charge of -1, and I have 3 of them, so that's really like a -3, which means my cobalt has to be a +3 so that it is neutral. Because it's neutral, I'm not going to put the word ion. These take practice to naming, so just keep that in mind. Alright, let's try doing some the other direction. I'll give you the name and then let's write the formula. Alright, so here I've noticed that there's no word ion, so I know this is a neutral compound. I also see that it's 2 separate words, potassium and then tetrachlorocobaltate 2. So potassium must be my positive cation, so I'm going to put K +1 because it's in group 1. Over here I have the element cobalt as my metal, so I'm going to put my brackets, and you always list the metal first, then the ligand. So the name and the formula are kind of swapped in the order. Chloro is chlorine, so Cl, and then tetra tells me I have 4 of those. Now I need to figure out what the charge is on my complex ion so that I can cross my charges. The Roman numeral tells me that the charge on the metal is +2, and I have 4 chlorines. Each chlorine is going to be a -1, so that's really like a -4. That tells me on my complex ion I have an overall charge of -2. So when I go to cross my charges, I'm going to cross the 1 and the 2. So my formula is K2COCl4. Notice the brackets instead of parentheses. So here notice that again the word ion is missing, so that tells me this is a neutral compound. The first one is my cation and my complex ion, and the second one is my element. So I know bromine is Br, and since it's in group 17 it's a -1. So now I need to figure out my cation. Since it's a complex ion, it's going to go in parentheses. Then I look for the metal. Here I have the metal platinum. Aqua is that special word for water as a ligand. Tricarbonyl. CO is carbonyl, so that has to go in parentheses, and then there's 3 of them because of the tri, so that goes on the outside. Now I need to figure out my charge on the complex itself. Platinum has a charge of positive 2 from the Roman numeral. Water is a neutral substance. Carbonyl is a neutral substance. So my overall charge here is +2. And then I'm going to cross my charges. So we would have Pt, H2O, CO3, and then Br2. Let's try one more. Alright, so here I have 2 separate words and no ion, so I know this is a neutral substance. Sodium is going to be Na, +1 because it's in group 1. Then I have my complex ion. So I'm going to put my bracket, I'm going to find my metal, ferrate. Ferrate is a Latin word for iron, so I know it's Fe. And then I look at my ligands. I have dicyanode, I know cyanate is Cn, and I have 2 of those. And then I have oxalato, which is one of those common, is the polyatomic oxalate, so that would be C2O4. And bis would be 2. And then I need to figure out the charge. So the Roman numeral here tells me that this is 3, so I'm going to say +3. Cn has a charge of -1, so there's 2 of them, so that's -2. Oxalate has a charge of -2, and there are 2 of them, so that's like a -4. So that means the overall charge, if I add that all together, would be a -3. So then I'm going to cross my charges, +1 and -3, and I get Na3, FeCN2, CO2, C2O4, 2.